Welcome guys to this online lecture on solar energy conversion. Now we'll deal with the unit number 5, PV system components and applications. And let's coming to the syllabus. It consists of three different parts. The first thing is a solar PV components. We'll discuss about the different types of components in a solar PV system, like solar PV arrays, inverters, batteries, charge controllers and net power meters. And then we'll discuss about the different types of plants, like solar central power plant, grid interactive plant, grid fallback type plant, standalone solar plant and hybrid solar plant. And we'll discuss some of the applications of solar for small applications. And then the third part of the syllabus is the design of PV system. That is how many for a particular load for your home, how many panels required, how many batteries required, what is the rating of an inverter. All these things we'll discuss in the last part. That is the design of a solar PV system. Now let's talk about the first part, that is the solar PV system components. The major component in a solar PV system is PV arrays, and apart from PV arrays, the remaining components are called the balance of system components. So inverters, batteries, charge controllers, net power meters, cables, wires, switches, enclosures, fuses, ground fault detectors, surge protectors, etc. All these things are called as the balance of system components. Except the solar PV arrays, the remaining all the components in a solar power plant are called the balance of system components. So for a typical battery storage solar PV system, the cost of the modules is only 20 to 30%, whereas the 70% of the cost is incurred for the balance of system components. So balance of system components are the major equipments in a solar PV system as well as the solar PV arrays. Now let's talk about solar PV arrays. We know that the number of cells connected in series is nothing but a module, and number of modules connected in series is nothing but a string, and number of strings connected in parallel is nothing but a array. You all know that in a module all the cells are connected in series. In a string all the modules are connected in series, and to increase the current rating we'll go for array. That is number of modules connected in strings connected in parallel is called a array. Now let's take a common example, general example. The diagram shows a PV array which consists of 4 photovoltaic panels. Here the arrangement is 2 by 2, which means 2 strings are connected in parallel and each string has 2 cells in series. Right. Here the voltage rating and current rating of each and every panel is 12 volts and 3.75 amperes. This 12 volts and 3.75 amperes are the VM and IM of a solar panel. What is VM? Voltage at peak power point, and current IM, current at peak power point. They are not the VOC and ISC. Right. A panel cannot be operated VOC and ISC, because if the panel is operated VOC, the current is 0. If the panel is operated ISC, the voltage is 0, and that's why we'll never operate the panels at VOC and ISC. In between there will be a maximum power point where we'll operate the panel, and the corresponding voltage is 12 volts and the corresponding current is 3.75 amperes. And what is the power rating of each and power rating of the panel? 12 volts into 3.75 amperes. Power is equal to voltage multiplied by current. We will get 45 watt panel. Right. So here what is the PV array? Now given array, what is the ratings of a given array? Total current and total voltage. Total voltage will be the voltage across the individual string. The voltage across a string will be, there are 2 cells connected in series and each cell will produce 12 volts. So in series we will get 12 plus 12. The voltage will get added up and you will get 24 volts across each and every string, and therefore the total output voltage from the array is 24 volts. And coming to the current, from each and every panel we will get 3.75 amperes. So from a string also, because they are connected in series, the current is constant. So from each and every string we will get 3.75 amperes. There are 2 strings, so total current is equal to IA plus IB, string A plus string B. So you will get 3.75 plus 3.75, which will be 7.5 amperes. So what is the total power or the maximum power that will be delivered by this array, total voltage into total current. So 24 volts is the total voltage and 7.5 amperes is the total current. So if you multiply these two, you will get 180 watts is the maximum power that you can draw from this PV array. The next important thing is the PV array characteristics. As you can see on the right side, you can see a PV curve. On the left side, you can see a IV curve of this PV array. Right. So you can see at the maximum voltage is 24 volts and the maximum current IM is how much? 7.5 amperes, whereas the peak power is 180 watts. You can observe it in the right side. At 24 volts, you will get the maximum power point voltage of wattage of 180 watts. So, but in practical conditions, because there are many variations like temperature variations, solar radiation variations, all these things, the output voltage, the output power of this array will be practically less than the 180 watts. And coming to the very important topic in this next in this photovoltaic arrays is the diodes. Diodes in a photovoltaic array. You can see there are two different types of diodes that will be used in photovoltaic arrays, which serves two different purposes. The first type of diode is called a bypass diode and the second type of diode is called a blocking diode. You can observe it. A blocking diode will be connected in series with a string, in series with each and every string in an array, whereas a bypass diode have to be connected in parallel with each and every photovoltaic panel of an array. In this case, there are 4 photovoltaic panels which are used in this array, and thereby you can see 4 green color bypass diodes connected across each and every panel, and 2 red color blocking diodes which are connected in series with each and every string. There are only 2 strings in this panel and in this array, and that's why you will get 2 blocking diodes. There are 4 panels in this array, and thereby you will get 4 bypass diodes connected in parallel to them. Right. So the type of diode which is used for blocking as well as a bypass diode is a Schottky barrier diode. The name of the diode which is used for these two purposes is Schottky barrier diode. The type of the diode and the nature of the work it will perform will vary, and we will see about that in the next coming slides. Now let's first see about the bypass diode. So generally, bypass diodes are used to reduce the power loss that solar panels experience due to shading. What is this shading? As I already discussed in the 4th unit, what is shading? Shading is nothing but if you keep a solar panel on a rooftop or on a ground, if some tree or a building's shadow fall on this solar panel, some part of the solar panel, in that part the voltage will not be generated. In the rest of the on the rest of the panel where the shadow was not fallen, the power will be generated. So it is what is called shading. Because of shading, the voltage and the power ratings will drastically come down. So what happens whenever shading occurs? Whenever shading happens, whenever a shade of a tree or a building falls on a photovoltaic panel, this panel consists of number of cells connected in series. Say for example, in one of the cell, on one of the cell a shading has been formed. So on that particular cell, from that particular cell, if it is a partial shading, we will get a partial voltage. If it is a complete shading, the voltage will be 0. Right. So current, we already know that current always flow from high voltage to low voltage. So the cells in a panel where sunlight is falling straight away will give you a full voltage, say 0.5 from a single cell. So let me talk about 0.5 volts. But the voltage which is produced from a shaded cell will be less than 0.5, maybe around 0.2 or 0.1 volts. So in the same module, we are having 2 different cells which are producing 0.5 volts and 0.2 volts. So what happens? Because of this potential difference, current will flow from 0.5 volts cell to 0.2 volts cell. Right. Current always flow from high voltage to low voltage. So, and what happens? This current, because of this flow of current from high voltage cell to the low voltage cell, this low voltage cell will act as a consumer of electricity instead of a generator of electricity. Actually it should generate the electricity, but in that place it is consuming the electricity, that is it is taking the current. So what happens whenever solar cell takes the current, when current passes through a cell, what happens, this causes the solar panel to heat up and have severe power loss, and this results in the formation of hot spots. This current flow through it and it results in the formation of hot spots. What are hot spots? Hot spots may result in breaking of the cells, detachment of the metal contacts, breaking of the glass cover, etc. So which would cause permanent damage to the PV module. You can see in the slide. So these are all the hot spots: breaking of glasses, detachment of metal contacts, breaking of glass cover over the panels. All these are the drawbacks of these hot spots. So hot spots are because of shading. Due to shading, the voltage produced by a cell decreases, and this leads to the flow of current from high voltage cell where sunlight is falling, that is unshaded cell, to the shaded cell. Current will flow from unshaded cell to the shaded cell, and because of this, that shaded cell will become a breakdown. That is what is called hot spot. Hot spot formed on these shaded cells, right? So in order to avoid these hot spots, we need to use a diode called a bypass diode. So we have to connect literally across each and every cell in a panel. In a panel, say for example there are 18 cells. Across the 18 cells we need to connect 18 bypass diodes, right? 18 bypass diodes. For the sake of simplicity, let me take four cells in a panel, and one of the cell 4 is shaded. So for all the 4 cells we need to keep the bypass diode. You may ask me a question, only cell 4 is shaded, why we have to keep bypass diode across each and every diode? Good question. The answer is, we don't know at what point of time what cell will be shaded. Now at 12 o'clock cell 4 is shaded. At 1 o'clock, maybe because of the movement of the sun, cell 2 might be shaded, and after some time cell 1 might be shaded. We don't know. So that's why for safety purpose we need to put a diode across each and every cell in a module or a panel. So when we keep this, what happens? Now whenever cell 4 is shaded, the diode which is connected across a cell 4 will get forward biased. That is, D4 is only forward biased, whereas the other diodes D1, D2, D3 will be reverse biased. So current always chooses the low resistance path. Whenever you make the D4 forward bias, the diode acts as a on switch and it will be short circuited. So it will provide a zero resistance path. So the current, instead of flowing through the cell 4, it will flow through the D4, and in that way the cell 4 will be saved from hot spots. That cell 4 will be saved from hot spots, right? We don't have to bother about these bypass diodes because they are already connected in parallel by the manufacturer itself. Whenever we purchase a panel, we will get this bypass diodes inbuilt, right? It is about the bypass diodes. It is about the panel level bypass diodes. One more thing is bypass diode placement. How the manufacturer will place the bypass diodes in a panel. So placing a block bypass diode across each and every cell in a module is very difficult, and it is not practical because of two issues. One is it is very complex, and the other one is too costly also. So it is not recommended also. So instead of that, a bypass diode is connected across a series of cells. That series of cells may be around 16 to 18 cells in a panel, right? If a panel consists of 32 modules, say 32 cells, say for example, so we will connect 2 bypass diodes. First 18 cells we will connect for 18 cells we will connect one blocking diode or a bypass diode. For the next 18 cells we will get one bypass diode. So you can see in the diagram, the bypass diodes from the unshaded cells are reverse biased and have no impact, the black color ones, whereas The bypass diodes from a shaded string is forward biased and conducts the current, and this current bypasses the movement towards the shaded cells, and that's why it is called a bypass diode. It will bypass the current without flowing through the shaded cells, and that's why it is called bypass diodes. Inside a panel they will be connected like this. Fine, it is about the panel. Now what about the outside of the panel? It is about a single cell, single module. Now we are talking about the string. A string means number of PV panels connected in parallel. In series. Number of modules connected in series is nothing but a string. Now we have a example, 3 different panels connected in series to form a string. All are connected in series. You can see end-to-end connection, right? The positive of the negative of first panel is connected to positive of second panel, and the negative of second panel is connected to positive of third panel, and so on. That's why all the 3 panels are connected in series. Now what happens whenever shading occurs on any one of the panel? Shading that shadow is fallen, so that particular solar panel stops generating the power, and because it is producing the less amount of voltage, the other 2 unshaded panels will produce more amount of voltage, and the current always obviously flow from generating panels to the shaded panels. That is unshaded panels to the shaded panels. Again there will be a hotspots formation. So to avoid that hotspots formation, we have to place the bypass diodes in parallel with every module in a array. That is why there are here 2 bypass diodes. One is the internal bypass diodes, which are connected across each and every cell in a module, that we need to do anything that automatically manufacturer of the panel itself will take care about it. But while taking the panel from the manufacturer and we are keeping them in a string, that is in series connection, we need to keep a diode across each and every panel. It is the what is called a bypass diodes, which we actually bother. Internal bypass diodes we cannot see, but these are the bypass diodes which we have to keep, right, to make the panels protective against shading, that is to prevent the hotspots. So in this way you can see that orange color line. So whenever the middle one is shaded, and that's why that the diode which is connected parallel to that middle panel is forward biased, whereas the rest of the 2, that is the left side and the right side panels are diodes connected across them are reverse biased, blue color, whereas this current, whereas the second one, whereas the middle one, the diode is forward biased. Now current is flowing, and you can see the current. So the current here, the current is not allowed to flow through the bypassed diode or the shaded panel. It is bypassed because the diode is on, acts as a on switch. So it low resistance part, and similar to the internal diode, and in this case also the current will flow through this external circuit without passing through that shaded cell, and thereby the panel is saved from hotspots. It is about the bypass diodes. And the second type of diodes is a blocking diode. A blocking diode will be connected in between a battery and a solar panel. Why we have to connect it between a battery and a solar panel? Say for example during the morning time, during a sunny day morning time, we have a solar panel and we have a battery. The voltage of the solar panel will be very high because sun is falling on the solar panel and we are getting the more and more amount of voltage, and on the other side we have a battery voltage. So which is bigger? On a sunny day, the voltage of the solar panels is more than the voltage of the battery, and thereby current always flow from high voltage to low voltage, and generally current will flow from solar panel to the battery, and the energy will be stored inside a battery. It is during the morning time. During the night times, what happens now? During the night times, sun is not available and the voltage generated by the solar panels is nothing, zero or very low. Whereas now the battery is fully charged during the daytime. Now the voltage of the battery is very high compared to the voltage of the panels, because there is no sun and there is no generation. Now current will flow backwards from battery to the panels. If it comes, there is two problems. If this backward flow of current takes place, there are two problems. The first problem is, as you said, hot spots will arise, the panels will be burnt out. And one more thing, the batteries from in which we have stored the energy will be drained out. If it drained out, then what happens? There is no energy which is left in the battery. Completely the battery will be drained out and we cannot give the energy to the load. That is the problem. And to prevent this reverse flow of current from battery to the panel, we will connect a diode called a blocking diode in between a panel and the battery. And you can see. Therefore, a blocking diode is placed in series between a battery and a solar panel string. And the blocking diode will only allow the power from solar panel to the battery. Whenever the power is flowing from solar panel to the battery, the diode acts as a forward bias and allows the current to flow through the battery. Whenever during the night time, whenever the battery voltage exceeds the solar panel voltage, the flow of current reverses. The current will now start to move from battery towards the solar panel, and this diode which is kept in between these two will act as a reverse bias and turn off the diode, and thereby acts as an off switch, and current will not flow through the solar panel. And that's why the battery and the solar panel both are saved. It is what about a blocking diode. So series parallel module interconnections. So let's take an example. In this example, there are n number of cells in a single string. A string consists of n number of cells. And how many strings are there? 3 strings are there. There are 3 strings, and each string consists of n number of cells. And you can see, because there are 3 strings, a blocking diode is connected in series with each and every string. A blocking diode is connected in series with each and every string, and a bypass diode is connected in parallel with each and every panel in a array. Each and every panel in a array. Therefore, number of blocking diodes is equivalent to number of strings in a PV array. Number of bypass diodes is equivalent to number of panels in a solar array. It is all about the solar PV array interconnections. In the next video, we'll talk about charge controller.